We're continuing our discussion of Millikan's oil drop experiment. Remember that previously we have found the charge on an oil drop is given by this expression, and then we have determined R and substituted for R our result in part B, which is this result, and we have obtained the final form of the expression for the charge on an oil drop. Now in part C, we have a set of data. You repeat the Millikan oil drop experiment. 4 of your measured values of the potential difference and the terminal speed are listed in the table. In your apparatus, the separation D between the horizontal plates is 1 millimeter. The density of the oil you use is 824 kilograms per meter cube. For the viscosity of air, we use the value 1.81 10 to minus 5 Newton seconds per meter square. Assume that G is equal to 9.80 meters per second square. Calculate the charge of each drop. Okay, so we're just going to substitute the numbers here. The charge on an oil drop is 18 pi. The separation between the plates, now I'm substituting 1 millimeters, 1 times 10 to minus 3 meters. The potential difference VAB, we will substitute from the table. And we have eta cube, which is the viscosity of air, 1.81 10 to minus 5 cube, the terminal speed cube, divided by 2 density of oil, 824 kilograms per meter cube, and 9.8 meters per second square gravitational acceleration, and this part is inside the square root. So when we substitute these numbers and calculate, we obtain Q is equal to 3.246 10 to minus 11 terminal speed Vt to the power 3 over 2 divided by the potential difference VAB. So if we substitute our set of values for the terminal speed and the potential difference, we will calculate the charge. So when we do that, for drop 1, so we're using for drop 1 these values, 9.16 volts and 2.54 10 to minus 5 meters per second. We obtain the charge Q to be 4.79 10 to minus 19 coulombs. So that's the charge of drop 1. For drop 2, we obtain a charge of 1.59 10 to minus 19 coulombs. For drop 3, we obtain Q3 is equal to 8.09 times 10 to minus 19 coulombs. And for drop 4, we obtain a charge of 3.23 times 10 to minus 19 coulombs. So that's the answer to part C. Part D, if the electric charge is quantized, that is, exists in multiples of the magnitude of the charge of an electron, then the charge on each drop is minus NE, where N is the number of excess electrons on each drop. All 4 drops in the table have negative charge. Drop 2 has the smallest magnitude of charge observed in the experiment. For all 300 drops on which measurements were made, So assume that its charge is due to an excess charge of 1 electron. Determine the number of excess electrons and for each of the other 3 drops. So the one that has the smallest magnitude of charge, we assume it has an excess charge of 1 electron. So we will calculate the number of excess electrons in the other ones. So let's see what happens here. In part D, we start with the assumption that the smallest charge, that is the charge of drop 2, is due to 1 excess electron. So that means the electron charge we're taking to be 1.59 10 to minus 19 coulombs. And the charge Q is equal to, in absolute value, the number of electrons times the electron charge, E. So drop 1 will have N1. The charge that we have calculated is 4.79 10 to minus 19 coulombs. So 4.79 divided by 1.59. If I get the closest, if I round it to the closest integer, this is going to be 3. For drop 2, the number is 1. That's what we're assuming. For drop 3, the number is, because we have charge 8.09, 8.09 divided by 1.59. That gives us a charge, a number of 5, integer value 5. And for drop 4, we have N4 is equal to, let's check the charge on drop 4, 3.23. So it is 3.23 divided by 1.59. This gives us 2. So these are the integer values that we will obtain for the number of excess electrons, assuming that charge is quantized in units of the electron charge. Let's look at part E. Use Q is equal to minus NE to calculate the electron charge from the data for each of the 4 drops and average these to get your best experimental value of E. Okay, now the first value for E we obtain is the charge on the first drop, Q1, divided by the integer we have rounded to. So we have 4.79 times 10 to minus 19 coulombs divided by 3, that is Q1. This gives us an estimate of 1.60 10 to minus 19 coulombs for the electron charge. The second value, E2, is Q2 divided by N2. Q2 divided by N2. And here we have assumed that we have 1 excess electron that is responsible for the charge. So 1.59 10 to minus 19 coulombs divided by 1. Our estimate of the electron charge is 1.59 10 to minus 19 coulombs. For the third drop, we have Q3 divided by N3, which gives us 8.09 10 to minus 19 coulombs divided by 5, and this gives us the third estimate, 1.62 times 10 to minus 19 coulombs. And for the fourth one, we have E4, it's Q4 divided by N4. The charge that we have obtained is 3.23 times 10 to minus 19 coulombs, N value is 2, so this gives us an estimate for the electron charge E4, 1.61 10 to minus 19 coulombs. How do we obtain the average value of the electron charge? The average value E is E1 plus E2 plus E3 plus E4, the arithmetic average, divided by 4, and this gives us an average electron charge, best estimate 1.61 times 10 to minus 19 coulombs based on this set of data. All right, so what we have done here is first, in the first part, we calculated the charge of the excess charge on an oil drop and found that we have this relationship between the charge and the viscosity, terminal speed, the potential difference between plates, separation between plates, density of oil, and gravitational acceleration. And then, using this set of data, we calculated the charge according to this expression on each drop. And then we assumed that this excess charge, and all of these charges are actually negative, so this is mentioned here. This charge is due to an integer number of excess electrons, and we assumed that the smallest charge that we have observed is due to one excess electron. So if this is due to one excess electron, then we can calculate the number of excess electrons for each drop by dividing it by this charge, and we round it to the closest integer to obtain an estimate of the number of excess electrons. Then we do the reverse. We calculate the electron charge based on the charge on that excess charge on that drop divided by this integer that we have calculated in part T, and we get an estimate of the electron charge, and we take the arithmetic average. We have our best estimate of the electron charge to be 1.61 10 to minus 19 coulombs.